Hi, everybody. So I wanted to take a few minutes to kind of go over chapter 10 or section 10.3 really quick. Just if you decide you want to try to work on that part or if you want to work through the study guide for the things that are on the complex plane. So here we go. We already talked about on Thursday that we have right here the imaginary axis, and over here the real axis is not red, it's real, really it is. We talked about how if I have the value, the complex value or the complex number, z equals 3 minus 2i, the real portion is the 0.3 and the imaginary portion is going to be that negative 2i part, so the negative 2. So if I plot that with the real axis here and my imaginary axis over here, I end up with a point that's right here. At that point in time, what we can do is we can start to think about this in a polar coordinate system where I have my magnitude or my modulus of z, and I write that, and it kind of looks like an absolute value of z, but that's actually the modulus of z. And we can define that using triangles. And remember here yesterday I used the Pythagorean theorem, and we found that that's equal to 3 squared plus negative 2 squared, which ended up being equal to the square root of 13. In class, I believe we used sine. Here I used cosine, so I know that cosine of theta, if I have some theta, which I didn't draw on there, this is my theta angle, is 3 over 13 because it's adjacent over hypotenuse, which means that theta is inverse cosine of 0.83205. Carried a lot of digits there. And we note that that's in the fourth quadrant. So I know it needs to be down there in the fourth quadrant, alrighty? So my cosine, inverse cosine, remember, will solve from 0 to pi. So that's 0 to pi. So I come up with 0.588 radians. Make sure your calculator is in radians. And my theta then is going to be 2 pi minus that, because I'm going to come down into the fourth quadrant, and I'm going to come up with 5.695 radians there. We did it yesterday with sine, and you saw how that worked out. Alrighty. All right. So the magnitude or modulus, as we said before, of z is denoted as what looks like the absolute value of z, kind of, the bars around the z, and it's the distance from the origin to the point x, y. We also talked about how we could use the conjugate, which is the opposite one, right? So if I have z equal to x plus yi, then the conjugate of z is x minus yi, at which point in time, we went through the FOIL yesterday, the two multiplied together, z and its conjugate, we get x squared plus y squared, which just so happens to be the same as what I have right in here on my Pythagorean theorem. So I can also define the magnitude of z, or the modulus of z, here as z times its conjugate, and then take the square root. And I think that's about where we left off. So if we want to actually convert this complex number from rectangular form to a polar form or an exponential form, we're going to talk about how we can do that. And first we're going to go to polar form. So I can use the same things that we've learned earlier in chapter 10, where we say the relationship between x, y, and theta is x equals r cosine theta, and y equals r sine theta. So then by substitution, what we can do is we can say z equals x plus yi. We have that as our given. That's our complex number. We can substitute in for x and y. So I have x, which becomes r cosine theta, plus r sine theta times I. Since both these terms have an r in them, I can factor that out. So I have r times cosine theta plus I sine theta, that whole quantity. So I can write my value for z in that form, and that's the polar form of a complex equation. we want to do that on the angle 0 to pi over 2, not including the pi over 2. And this is the argument sometimes of z is what we call this. Alrighty. So then, note that the magnitude of z is going to be equal to my r. Okay, that's my radius, which kind of makes sense. If we go back to this here picture, hold on, right here, this line is my modulus of z, or my magnitude of z. It's also equal to the radius if I think about a polar form. And then, so here I could write this like this. That's equal to r, and my theta right here is still equal to theta. Alrighty? Not overly complex, kind of straightforward. So if I want to look at the expression z equal to 3 minus 3 square root of I, and I want to plot that, then I'm going to be down in the fourth quadrant, right? Because this is my imaginary axis, and this is my real axis. So I'm going to be 1, 2, 3 over this way, 1, 2, 3 square root of 3, which is going to be 3 times 1.7 something or other. So we'll put it down. I'm going to think, all right, I'll actually multiply it. Hold on. It's about 5.19. So 1, 2, 3, 4, 5. So I'm about right here. Okay, this is z equal to 3 minus 3 root 3 of I. That I is outside of the square root. Notice this is in Q4, right? If I'm going to draw our modulus of z, right? And this is right here. Actually, I want it on 0 to 2 pi. So actually, my angle is more going to be like this. Okay, this big angle. Alrighty. Oops, wait, let's try that again. Hold on. It's going to be from the real axis. It's going to be from the real, oh, I'll get it. It's going to be from the real axis around. Sorry about that. All right, so that's my theta. There we go. So it's between 0 and 2 pi. All right, so if I want to find r, then I can say that r equals my modulus of z, which is going to be equal to the square root of 3 squared plus, I still like the regular Pythagorean, but you can imagine that it's the same as what that z and its conjugate is. It's the same end result as x squared plus y squared. So I'm going to come out of this with 9 plus 9 times 3 is what that'll be. So I'm going to have the square root of 9 plus 27. I'm going to have the square root of 36, which is going to be equal to 6. All right, handy dandy. And then the second thing that we can do is we can calculate. So I'm going to have cosine theta, for my case, just because I like that real number, is equal to 3 over 6. That's not a 6, which is equal to 1/2. That means that cosine theta, or theta, is equal to inverse cosine of 1/2. And so I have a theta, if I look on my range for inverse cosine of 0 to pi, equal to pi over 3. So I really want to go all the way around into Q4. So what I'm going to do is I'm going to take theta equal to 2 pi minus pi over 3, because I know that this angle right here is pi over 3. Actually, it's negative pi over 3. And so what will come out of it here is 5 pi over 3 if I look at my theta from 0 to 2 pi. Right? Not too bad, right? I can write then my equation. I'm going to kind of try and squish it in here. So I can write my equation where I say, I'm going to write it up here. Z is equal to 3 minus 3 root 3I, which is also equal to R, which is 6, times cosine of 5 pi over 3. And then I'm going to say plus, let's put the I first, I sine of 5 pi over 3. Okay, so this is really me writing it in polar form right up here, just so I have room. All right, not too bad so far, right? If we look at Leonard Euler, who established a relationship known as Euler's formula between complex numbers and the number e, another reason to like e's. For any real number theta, then e, here we'll expand, e I to the I theta is equal to cosine theta plus I sine theta. That's something fun to prove, go for it. So then that means that we can write the polar form of a complex number using exponential notation, and we have this beauty right here where I have R of cosine theta plus I sine theta is equal to R e to the I theta. Okay, when we write it in this form, we say it's written in exponential form. Makes kind of sense, right? The one right here is polar form. The one right here is exponential form because I have exponents. Note that Euler's formula, theta is a real number, so it's got to be, or theta is a real number, and theta has to be in radians. So knowing that, we can use the information from the very last part where we had found R was equal to 6 for this Z equals 3 minus 3 square root of I. We had also found out that theta was equal to 5 pi over 3. And so we can make a long drawn out set of equivalencies where we say Z equal to 3 minus 3 square root 3 of I is equal to 6 times cosine, because that's our x, 5 pi over 3, plus I times sine of 5 pi over 3. If you're wondering whether that should be a negative sign, it should not be, because sine of 5 pi over 3 will be a negative number. So that takes care of the negative for us. If you need to go backwards, like multiply this through right here, and you'll come up with your original equation there. And this all is equal to, whoops, let's put the 6, my radius, e I to my 5 pi over 3. Okay, so all of that goes up there in that exponent, and that is my exponential form of the complex number. All right, let's see. If I look, we've got some examples here where we plot things in the complex plane and write an expression for z in rectangular form. You can go ahead and try and bring those back if you want to. I'm not going to do the example right now. Maybe we'll do that in class on Monday. If we look at the exponential form of a complex number, it's really useful. That's why we're going this way. That's why we do polar numbers. That's why we do all of this craziness with changing to exponential or polar form. Is it's easier to deal with in a given situation. So the exponential form of a complex number is useful for finding products and quotients of complex numbers. It's also useful for finding, if I want to find the square or the cube or the fourth or to the fifth or a root, okay? So the first theorem here is suppose Z1 is equal to R1 EI to the theta 1, and Z2 is equal to R2 EI to the theta 2, and those are two complex numbers. Then it shows you that what I can do there is I basically multiply together these two things, which gives me my two radii multiplied together. And then remember, we add when we multiply two exponents or two values that have the same base. I add together my exponents. So if you want to look at the step-by-step between this, we have R1, R2, E, I theta 1 plus I theta 2, and then they just factor out the I. Okay. If I'm dividing and assuming that my complex number 2, Z2, does not equal 0, which is always a good thing not to do, don't divide by 0, then we have R1 divided by R2, and we subtract those exponents. So remember that when you divide, like this part right here, the exponential part there, we always subtract. So the in-between step there becomes R1 over R2 E I theta 1 minus I theta 2, which then comes back up to that very equation right there. Alrighty. So if I want to multiply my z and my w here, you can see that that looks a little daunting. I'm multiplying all sorts of weird things with sines and cosines and i's, and that's an awful lot in my world. So I would start out by changing them both to exponential form. So I have z is equal to 3 e to the I of pi over 9, which doesn't look nearly as bad. And I would have a w equal to 5 e to the I of 5 pi over 9. Very important that they're in radians. So zw is going to be 15 ei to the pi over 9 plus 5 pi over 9. I multiplied those two radii real quick in my head. It wasn't that hard. So we end up with 15 ei. I'm going to end up with a 6 pi over 9. This is the hardest part, which is going to be equal to 15 e to the I, and then we're going to have a 2 pi over 3. When I reduce that fraction, be sure to reduce those fractions. I like that 2 pi over 3 way better than 6 pi over 9. If I look at the division problem, then z over w, my modulus, my radius, whatever we want to call it, is going to go out front. So I'm going to have 3/5 e I to the z's on top. So I have pi over 9 minus the 5 pi over 9. So that's going to be 3/5 e I to the negative 4 pi over 9. We can change that into a positive number if we'd like to. That's going to have an 18 pi added to it because that's what 2 pi is. So I'm going to have a 3/5 e I to the, I believe, 14 pi over 9. An ugly number, but it is what it is. All right. So I'm making sure that one's right there. For some reason, my brain is not quite there with it. Okay, not so bad. So those look good. Certainly makes it a whole lot easier than if I tried to imagine coming back up here and trying to FOIL these things. I think I would rather do almost anything else. So this is a lot easier method than foiling those things. All right. Notice the solution of the previous example demonstrates that the argument of the complex number is periodic. So we still have a periodic argument here. So notice that, and actually I did that right here, RE I to the theta is equal to that plus 2 pi, or 2k pi, 2 pi k, I usually put the pi out front, where k is any integer. So right up here, I added a 2 pi to it, just to make it be in the range that I want it to be. If I came out with, let's say, a 25 pi over 12, I wouldn't want to leave it like that. That would be really messy and ugly. All right. The next one, I'm going to skip over the exploration real quick. I'm going to show you, I'm not going to say it, de Moivre's theorem. If z is equal to r e to the I theta is a complex number, then we know that if I take my complex number to the power n, z to the n, then I end up with that being equal to r to the n times e I to the n. This makes sense. If I pop the things into the middle, it's probably what happened up above. Then I had r e I theta. Here was my z value. I'm taking that to the nth power. Whenever you do that, you multiply whatever the exponent is up there. So I have r to the n, e, I, n, theta. Exactly what we had. They put this in parentheses. All right. So that, oh, in rectangular form. Okay, sorry. I didn't read all the way. All right, so first we would plot this, we would write it in polar and then exponential form. If you'd like to run through that, you can feel free. Let me give you what you should get out of that. You should get an r equal to the square root of 1, really? 1 plus 3, which is the square root of 4, which is just 2. So I'm going to have a radius of 2. At this point in time, I get a cosine theta. Again, I like cosine because I like that real part there. There's no root, is equal to 1/2. So theta here is going to be equal to pi over 3, similar to what we did in the last one, right? Again, I know if I were to plot this real quick, it's somewhere down here. So I'm in Q4. That's why we plot it. That's why it says to plot it. So I want this in Q4, so I have a theta equal to 5 pi over 3, yet again. All right, all I did was take 2 pi minus pi over 3, because I want to be in Q3, or Q4, sorry. So I come up with 5 pi over 3, right? All right, so I know then that that means if I write this in polar form and then exponential form, I have a z equal to 1 minus the square root of 3i to the 10th is equal to, we're going to put big parentheses here, 2 times cosine of 5 pi over 3 plus I times sine of 5 pi over 3, all to the 10th power. That I do not desire to do, so I'm going to write this in exponential form. I'm going to say it's 2e to the I theta, and I'm going to use the 5 pi over 3. I'm going to take all of this to the 10th power now. All right. I suppose this one didn't really need us to the 10th power since it said just to write it, but now I'm going to actually do that. So if I want to raise it to the 10th power and simplify my answer, I'm going to get z equals 2e I to the 5 pi over 3, all to the 10th power. So I'm going to have 2 to the 10th e I to the 10 times 5 pi over 3. If I look at 2 to the 10, I end up with 1024. And the EI to the 50 pi over 3, well over my pi over 2, right? So if I continue to subtract off, well over my 2 pi up here, right? This is way too big. I have no idea where that is off the top of my head. So I continue to subtract off 6 pi over 3, that's a 2 pi value, until I get a 1024e to the I of 2 pi over 3 is what you're going to come out of there with, all right? If we use our calculator, oh, wait, let's take this back into our other form. That means that we have 1024 times cosine of 2 pi over 3 plus I sine of 2 pi over 3. All right. I can take this back even further, back to rectangular form, which is what I wanted up here. So I have 1024 times cosine of 2 pi over 3 is going to be negative 1/2. And then I'm going to be plus I sine of 2 pi over 3. It's over there in the third quadrant. It's going to be root 3 over 2. So I'm going to end up with negative 512 plus 512 root 3I. Alrighty. If you'd like to use your calculator to confirm this result, go to mode. About the 7th one down, what you'll see is a thing that says A plus BI. I think it has standard or something written. Let me look real quick here. It has real A plus BI or RE to the theta I down there in that row. So pick the A plus BI, and then you can type in 1 minus square root of 3I to the 10th. You should get the result out that you have here. All right. I'm going to let you do the next example yourself if you would like to, or we can work on it a bit in class. In previous courses, note that when we're asked to solve the x squared equals 4, we end up with 2 answers, right? That's because we have the plus or minus values of x that are given when basically plus or minus 2 is equal to, when squared is equal to 4. So if we suppose that w is a complex number and n is greater than 2 is a positive integer, then for any complex number z that satisfies the equation z to the n equals w, the complex nth root of w. That's the complex nth root of w, the z is, okay? So in keeping with the previous usage, basically we're going to look at complex square roots when we have, our z would be the complex square root of w. Here z would be the complex cube root of w, and so on. To find all of the roots of a complex number, the following theorem is used. So if we have w equals re to the I theta, again you see that's my complex number in exponential form, and n greater than or equal to 2 is an integer, and assuming that w does not equal 0, so we don't just have a 0. There are n distinct complex roots for w given by the formula z sub k equal to the nth root of r e I to the 1 over n theta plus 2k pi, where k equals 1, 2, or 0, 1, 2, and all the way up to n minus 1. All right, so that's wonderful. If we look at, if we run through just a little bit the complex roots of that, oh, this time it's a negative 3 plus root 3i. So in this case, we're actually, in the second quadrant. Let's try this whole thing again. There we go. We're in the second quadrant here. So we're at negative 1 root 3. So I'm somewhere up here. All right. So if I look at my radius, I'm going to have a radius equal to the square root of negative 1 squared plus root 3 squared, which is going to be equal to the square root of 4, which is going to be equal to 2. Again, cosine theta, I like it just because of the real part and not a square root, is equal to negative 1/2 this time. I know I'm in Q2. So I'm going to want a theta that's in Q2. That means that my inverse cosine I can just use. So that means that cosine theta is going to be equal to 2 pi over 3. Okay, so I can write my complex number z equals negative 1 plus square root of 3i in my exponential, polar and exponential form. I'm going to use polar first. That's equal to 2 times cosine of 2 pi over 3 plus I sine of 2 pi over 3, which is equal to 2e to the I times 2 pi over 3. All right, now we're going to find z sub k by using the complex root theorem. So remember, z sub k is equal to the nth root of r e I to the 1 over n times my theta plus 2 pi k. So I'm going to leave that k in there for right now, okay? All right, so here my n, because I'm looking at the fourth roots, n is going to be equal to 4. And remember, that means that I'm going to have n minus, well, I'm going to have n roots, but I'm going to go up to z sub 3, okay? Because z sub 0 counts. So I'm going to have, coming out of this, when I come down here, I'm going to have this, these are all my roots of this for the fourth roots, because I'm going to have 4 options, all right? All right, so let's sub in. So I have z sub k is equal to the fourth root of 2. I'm ready to write that too. The fourth root of 2, e I to the 1 over 4, because I'm taking the fourth root. My theta is 2 pi over 3 plus 2 pi k. So this is all equal to the fourth root of 2, e I'm going to distribute that 1/4 just because I don't like it there. So I've got a 2 pi over 12 plus a pi k over 2. Just you know what? I'm going to leave the 2 pi k up there. I'm changing my mind here. So I'm going to leave it as a 2 pi k over 4. I'm going to get a common denominator up here because otherwise this is going to be a pain to deal with as we get these roots. So I'm going to do one more step. I'm going to say this is equal to the fourth root of 2 e I to the 2 pi plus 6 pi, right? 6 pi. Am I thinking right? Multiplying top and bottom by 3. I have a different number on my thing. 1/2. Yeah, it's going to be 6 pi k over all of this over 12. Look, my notes are wrong. All right. So that means that if I look at this, yeah, I see what I did. Okay, that means that z sub 0 is going to be, I'm going to put in everywhere I have the n, or I'm sorry, the k, thank you, z sub k, because these are equal to my z sub k's. Everywhere I have a k, I'm going to put in the 0. So here I'm going to have, hold on, I'm in erasure mode. I'm going to have the fourth root of 2 e I to just the 2 pi over 12, which is going to be the fourth root of 2 e I to the pi over 6. Right, so that's my first one. Strangely, I wrote that part right. C sub 1, I'm going to substitute in a 1 for my k value. So I'm going to have the fourth root of 2 e I to the 2 pi plus 6 pi times 1 over 12. So here I'm going to get the fourth root of 2 e I to the 8 pi over 12. So here I've got the fourth root of 2 e to the I, and I'm going to have a 2 pi over 3. Right? Yep. Z sub 2 is going to be the fourth root of 2 e to the I, and this time I have 2 pi plus 6 pi times 2 all over 12. So that's going to be the fourth root of 2 e I to the, this one will be 12, 13, 14, so I'm going to 14 pi over 12. So that's going to reduce a little bit to fourth root of 2 e I to the 7 pi over 6. I'm still on 0 to 2 pi. Notice that, okay? I'm over pi, but I'm still under 2 pi. My very last root is e sub 3, because now I have 1, 2, 3, 4 roots here. So I have the fourth root of 2 e to the I, and I'm going to have 2 pi plus 6 pi times 3 this time over 12. And that's going to give me the fourth root of 2. Oopsie. Sorry. Fourth root of 2 e to the I, and this time I have 18 plus 2, so I'm going to have 20 pi over 12. That's going to reduce to 10 pi over 6, or 5 pi over 3, which is going to be the fourth root of 2 e I to the 5 pi over 3. All right, so those are my 4 roots. This one right here, this one right here, this one right here, and this one right here. The 4 complex roots for my my complex value, where -1 plus the square root of 3i. All right, that wraps it up. I think it'll do it. Sorry it was so long. I wanted to get through this just so that you can watch it if you're looking to do the homework, or if you're trying to do that study guide. Have a great day.